It is November 1991, and Williams Grand Prix engineering has a problem. Not a small problem, a structural one. Their car has just lost a world championship it should have won. Nigel Mansell had one of the fastest machines in Formula One, yet retired from 5 races, not because the car lacked speed, not because the drivers lacked talent, but because Williams was trying to make a racing car do something Formula One had never fully mastered before. The car was becoming too advanced for its own reliability. Hydraulics, software, sensors, electronic control, active suspension, semi-automatic shifting, traction control, all of it was there, but not yet working as one complete system. The hydraulic actuator seals had not been tested under the thermal cycling conditions of a full race distance in the Malaysian heat. The software was hunting, searching for a ride height target and occasionally overshooting it mid-corner at 180 kilometers per hour without any input from the driver. The idea was correct. The execution was not finished. By the end of 1991, Williams knew something important. They had not failed because the idea was wrong. They had failed because the idea was not finished. And in 1992, they finished it. This is the story of the Williams FW14B, the car that made the rest of Formula One look like it was competing in a different era. To understand the FW14B, you have to understand what active suspension really meant. A normal Formula One car rises, dives, rolls and pitches as it moves through a lap. Under braking, the nose drops. Under acceleration, the rear squats. Over bumps, the body moves. Through fast corners, the car leans under load. For a driver, this is normal. For an aerodynamicist, it is a nightmare, because the underside of a Formula One car is extremely sensitive to ride height. If the floor is too high, the car loses downforce. If it is too low, airflow can stall, a phenomenon called diffuser stall, where the aerodynamic seal between the floor and the track surface breaks instantly and downforce disappears faster than any driver can react. The difference between perfect grip and sudden instability can be just a few millimeters. Most teams solved this by compromise. They ran the car high enough to avoid danger, even if that meant giving away performance. In 1992, that compromise was worth approximately half a second per lap at a typical circuit. Williams wanted to eliminate that compromise entirely. They wanted the car to hold the perfect ride height all the time, under braking, through corners, over bumps, with full fuel, with low fuel, on new tires, on worn tires. That was the revolution. Lotus had experimented with active suspension in the 1980s, even racing versions of it with Ayrton Senna in 1987. But those systems were mostly reactive. They responded after the car had already moved. By the time the correction arrived, the disturbance had already propagated through the chassis. Williams wanted to go further. They wanted a system that could control the car continuously before the movement became a problem. Patrick Head, Williams' technical director, understood the risk clearly. A Formula One car with a malfunctioning active suspension system at 280 kilometers per hour is not a car with a handling problem. It is a projectile with a software fault. So Williams did not rush it. They developed the system for 4 years. Then Adrian Newey joined Williams. Newey understood something crucial. Active suspension was not only about handling, it was about aerodynamics. If the suspension could keep the car at the perfect height, then the entire floor could be designed around that height. The underbody would work more consistently. The diffuser would stay in its ideal window. The wings and floor would no longer be fighting against a constantly moving chassis. Newey designed the FW14B's underfloor geometry around ride heights that no passive car could safely maintain, and then the active system held those heights lap after lap, regardless of what the track or the fuel load demanded. The FW14B was not simply a fast car with clever suspension. It was an aerodynamic system built around active control. The software was the key. Earlier systems tried to control too many things through one response. ride height and wheel damping were treated together, even though they needed different behavior. Ride height needed fast, forceful correction. Wheel control needed smoother, more delicate movement. Running a single control loop with a compromised response meant the system was never doing either job correctly. The breakthrough came from Paddy Lowe, then a Williams engineer, who would later lead the team's technical operations. Lowe separated the two functions entirely. One control loop managed ride height, another managed wheel movement. A supervisory system balanced the two. This seemingly small architectural change eliminated the hunting behavior that had plagued earlier versions and transformed the active system from a sophisticated experiment into a race-winning tool. The hardware was just as serious. Hydraulic actuators at each corner of the car were capable of exerting forces of approximately 8,000 newtons, moving at 200 millimeters per second. Position sensors measured suspension movement to an accuracy of 0.1 millimeters. A custom onboard computer, weighing 3.2 kilograms, roughly the size of a hardback book, processed data at 500 times per second. The hydraulic pump maintained a working pressure of 200 bar throughout the operating range. Every single component in this chain had to survive 60-degree cockpit temperatures, 5G cornering loads, and the vibration spectrum of a Formula One car at full speed. Nothing about this was simple, nothing was off the shelf. The first time Nigel Mansell drove the completed FW14B at Barcelona in early 1992, he immediately understood that it was different. Drivers often describe good cars as feeling connected, balanced, or predictable. Mansell said this car felt like it was on rails. That phrase is used often in racing, but in this case it was almost literal. The FW14B did not move like a normal racing car. It did not argue with the driver. Mansell turned the wheel, and the car simply went where it was asked to go. There was less negotiation between man and machine. There was execution. During testing, Williams was not even pushing at maximum performance. They were validating systems, using conservative settings. Even then, the lap times were 1.8 seconds faster than the circuit's existing track record. The team said little publicly. They packed up and prepared for the season. Then came Kyalami, the opening race of 1992. Mansell took pole position, led from the start, and won by 24 seconds. But the real shock was in the data. The suspension traces showed the car holding its ride height to within plus or minus 2 millimeters throughout the entire race. Across changing fuel loads, tire wear, braking zones, fast corners, slow corners, across 72 laps and 180 kilograms of fuel burned, the aerodynamic platform stayed stable. For Newey, this meant the car on track was finally behaving like the car in the wind tunnel. The simulation and reality were coming together. That was the real advantage. Mansell won the first 5 races of the season. The margins were not normal. At the Spanish Grand Prix, he set a fastest lap 1.4 seconds quicker than the second fastest car on the circuit, a gap so large that the timing systems were checked by officials before the results were confirmed. Ayrton Senna, one of the greatest qualifying drivers in history, was sometimes left more than a second behind in a McLaren Honda that was, by any objective measure, receiving the finest normally aspirated V12 engine Honda had ever produced. This was not only engine power, it was not only downforce, it was integration. The active suspension kept the car stable, the traction control helped manage power delivery. The Renault RS3C V10, producing over 710 horsepower in race trim, with qualifying specifications approaching 760, was matched to a semi-automatic gearbox that shifted in 18 milliseconds compared to the 50 milliseconds of a conventional manual change. Every system strengthened every other system. That was what made the FW14B terrifying. Its traction control was especially clever. It did not simply wait for wheel spin and then cut power. It predicted the conditions where wheel spin was about to happen and adjusted engine delivery smoothly, modulating ignition timing and throttle position before the wheel speed sensors detected actual slip. To rivals studying the car from outside, there was no obvious sign of intervention. It looked like Mansell simply had incredible traction, and he did, but not by himself. The semi-automatic gearbox added another layer. Instead of using a traditional manual shift, Mansell changed gears with paddles behind the steering wheel. The system shifted faster than a human could, and more importantly, it allowed him to keep both hands on the wheel through every corner. Over a race distance of 1,000 tons in 200 gear changes, that mattered enormously, not just mechanically, but cognitively. Every task removed from the driver allows more focus on braking, turning, positioning, and attacking. In the FW14B, the car took away many of the distractions. Mansell could trust the machine, and the machine was almost always right. The result was domination. Mansell secured the 1992 World Championship at the Hungarian Grand Prix, with 5 races still remaining. The earliest championship clinch, by calendar date, that Formula One had seen in the modern era. By the end of the season, he had won 9 races and taken the title by 52 points. But the FW14B was not only dominant when everything was perfect, it was also remarkable when things went wrong. At Silverstone, Mansell suffered a right rear tyre deflation at Woodcote Corner at approximately 290 km/h. In a conventional car, that kind of failure at that speed would almost certainly have caused a spin. The active suspension system continued functioning, reallocating hydraulic pressure across the 3 remaining corners, attempting to maintain overall chassis balance. Mansell managed the situation, brought the car back to the pits, rejoined in 5th place, and drove to 2nd, setting the fastest lap of the race in the process. To the crowd, it was a heroic piece of driving. To the engineers reviewing the active system logs afterward, it was proof that the control architecture could survive conditions it had never been designed to face. Both were true. That is what made this car special. The FW14B was retired at the end of 1992. By then, Formula One's governing body had seen enough. For 1994, active suspension and all electronic driver aids were banned outright. The official reason was sporting fairness. The simpler truth was this: Williams had built a 4-year head start that no rival could close within a single season. So the rules changed. Yet the most important thing the FW14B created could not be banned. It changed how Formula One thought. It proved that a racing car was no longer just an engine, a chassis and a driver. It was a system, a complete network of aerodynamics, electronics, hydraulics, software, data, and human input working as one. Every modern Formula One car, every control system, every data channel, every sensor array exists in the world the FW14B helped create. 2 millimeters, that was the difference. 2 millimeters of ride height control, maintained 500 times per second at almost 300 kilometers per hour. That was the FW14B. Not just a fast car, not just a clever car, a car so advanced that Formula One had to change its rules to catch up with it. And that is why, more than 30 years later, the Williams FW14B is still remembered as one of the most technically important racing cars ever built. If you found this useful, subscribe. There are more stories like this one in the archive, and more coming. Leave a comment below. Which car should we examine next? The Brabham BT46B that was legal for exactly 1 race, or the Ferrari F2004 that ended an era?